Okay, so once you have all those definitions written down about concavity and so forth, we need to do some examples. So we're going to limit this function to between 0 and 2 pi. Those of you who are watching the video, you just need to make sure you know what the first derivative test is, what the second derivative test is, and what concave up and concave down is. Get all that from the textbook. But here we are from 0 to 2 pi. If I were to graph this from 0 to 2 pi, we can do it without our calculator, right? There's pi, pi over 2, 3 pi over 2. There's 2 pi, go up 1, 2, 3, and then it's going to go 1 above that. So I have a new midline. That's a good review. New midline at 3. Is it going to start on the midline here? And it's going to go up and down to the midline, down right there, and then so there's one cycle. So you could visually tell me it's concave down from 0 to something pi. But it's concave down in there, and then it's concave up also one time between pi and 2 over pi. Over which interval is this function concave up, concave down? So how are we going to figure that out? When in doubt, take the derivative here. So f prime of x equals cosine of x. I'm only asking about concavity here. That's it. So f prime is cosine of x. That's not what I'm going to use for concavity. I'm going to go to f double prime. So second derivative is equal to negative sine of x. So f double prime of x is equal to negative sine of x. And then I'm going to do the same thing I did with the first derivative. I'm going to set it equal to 0. Okay, so 0 equals negative sine of x. This isn't going to be revolutionary. You're just going to find what you already see in the picture. We're going to calculate. So what does x have to equal? I could divide out the negatives, so 0 equals sine x. So where on 0 to 2 pi is x equal to? We've got x equals inverse sine of 0 just on 0 to 2 pi. So x would equal what? Where's the y coordinate? 0. Between 0 and 2 pi. So, and if it's a closed interval, it's actually at 0 pi. But 0 and 2 pi are the endpoints of the interval. So really, we're just testing at pi. So our intervals go like this. We have interval. So go ahead and write interval. You got interval here. The intervals are 0 to pi and pi to 2 pi. And then we want sine, this time sine of f double prime. So if sine of f double prime is positive, it's concave up on that interval. If it's negative, it's concave down. So what would be a good test point here? F double prime of, what's a point you could plug in without even using a calculator? Maybe pi over 2? Would that work? Pi over 2? Pi over 2 is between 0 and pi. Nothing changes in terms of concavity between 0 and pi. That's what the calculus says. Nothing changes. So I could pick any point between 0 and pi and plug it into the second derivative. And if it comes out positive, it's concave up on that whole unit. That's it. And if it comes out negative, it's concave down. So f double prime of, let's see here, we got pi over 2. We get, so we've got f double prime of pi over 2. And then here we could try f double prime of maybe 3 pi over 2. Let's go ahead and plug it in. That's what we get. So go back to f double prime. I'll box it here. What is f double prime of pi over 2? Negative 1. Sine of pi over 2 is 1. I got the negative out here. So this is negative. Are we there? I'm plugging it in right here. I can show it here. It looks like this. It'd be negative sine pi over 2 equals negative 1. And that gives me that negative sign. And then right here, I've got negative sine of 3 pi over 2, which is negative 1 or positive 1. So that's positive. So then I can answer the question. It's exactly what I see up here. So it's concave down from 0 to pi. So concave down would be on the interval from 0 to pi. And go ahead and leave open brackets for concavity. And then concave up is from pi. So from pi to 2. That's it. That's the concavity. That's how you figure out concavity from the second derivative. So finish writing that down. And we're going to put it all together in the next example. So I'm going to do one more example, and then I'm going to let you take your test. So we'll put all together the next example. And you're going to go through, so those of you who aren't taking a test can go ahead and work on the homework. You're going to run into functions that are harder than the polynomial function I'm going to give you, okay? But what makes it harder is the algebra. So that's it. The process is the same, no matter what. So I'm going to give a fairly straightforward one, a polynomial example. The only thing I could really warn you about, or what I would warn you about, is don't forget to check where the derivative does not exist. Don't forget to check where the derivative and original function do not exist, because that will help to break up your interval in these interval tables you're making. So don't forget about that. You won't have any trouble setting the derivative equal to 0. And, well, you might have some trouble doing the algebra, but setting equal to 0 and solving. But that's the only difference between these examples. So the definitions, the rules are all the same. It's the algebra that's really hard. So you have to just try this 5-3 homework with the harder functions in it, and then come and ask me about them, because I can point out different things on it. So one more note here. The point at which the graph has a tangent line and changes concavity is called the point of inflection. So here, the point of inflection is, yeah, it's exactly pi. X equals pi. So if you could write that down, the point at which the graph has a tangent line and changes. The fact that it has a tangent line means it's differentiable. And changes concavity is called the point of inflection. So once again, we're only listing the x coordinate of the point of inflection. If you're asked for the y coordinate, what would you do? Plug it in. Plug it in where? Original. But usually they don't ask. Oftentimes it's just what's the x coordinate, especially when we're just doing like practice. This is just skill-based practice. You have to find y when you get to the real life problems, which start in 5-4. Go to 5-6. We're going to do optimization, related rates, and local linearity. Those are the 5 topics. All right. Got this? The point at which the graph has a tangent line and changes concavity is called the point of inflection. So the point of inflection here is x equals pi. So now we're going to put it all together. I'm going to ask you maxes and mins, increasing, decreasing intervals, concavity intervals, and point of inflection. That's everything. That's a function. Do that for this guy. Oh, here lists the second derivative test. This is pretty cool. If f double prime of c is greater than 0, that's taking the critical point that you got from the first derivative. You take the critical point you got from the first derivative, that's what c is, and you plug it into the second derivative and you get a positive number. Then at that point, you have a local min. Here's how I think about it. That makes sense to me. The fact that f double prime is positive means it's concave what? Here's my picture. So does it make sense that that's a local min at that point C? Does that make sense? And f double prime less than 0, that says the second derivative is negative. So that that's where C is there, and it's a max in that case. That's the second derivative test. It's a pretty slick way to do it. If you really want to be efficient, second derivative test is going to be. But first derivative test. So putting it all together is what they're going to ask you to do. Yeah, you'll have so keep you busy between hunts. This assignment's kind of long. It is. School Mondays for calculus. Just find everything that I just mentioned. So we're going to find everything. I don't know that you need to write all that down. You're going to find everything. You're going to go through this process. I think what they do in the book is they do build up to it. They ask some questions where they just ask for parts of these, and then by the end problems, they ask you to do everything. First of all, we should consider domain. Okay, just which is negative infinity to infinity. As a matter of fact, the domain of every derivative will be that. But you got to think about domain. Don't forget about that. Find the first derivative. There's the first derivative by the power rule. And then find the second derivative. Just you might as well do that right away. And then my other suggestion would be, contrary to what I've told you through chapter 4, is you do want to try and simplify some things. If you have rational expressions, you want to get it as a single rational expression. Like if you can move negative powers down to the bottom and put the radical over it, you want to do that. Because what's going to happen algebraically is you're going to set it equal to 0 and you're going to move one of those terms over. And you'll have a lot of product rule sort of things to deal with. So you will want to maybe do some simplification. You may even have to simplify the first derivative before you go and get the second, or you'll make just a mess for yourself, an algebraic mess. So just be aware of that. But with this, we don't have to worry about it. Okay, and then we're going to set the first derivative equal to 0. And solve it. A lot of these are factorable. This one is. So we got 3x and x minus 5 plus 1. So they're mostly factorable. In the textbook, they have a little gray shading over the ones that you should be able to do without a calculator. So that means quadfactorial. I think if it was quadratic formula, it would be unshaded. So you have to use a calculator to get the decimal approximation. Okay, so x equals what or what? We got 5/3, right? Or x equals -1, and we call those critical points. Those are C's. Those are critical points. Just put a little note there. Those are critical points. It's going to help break up my interval table. Okay, so we're going to make one interval table that's dealing with the first derivative. It looks like this. We've got interval. And we've got sine of f prime. And I will get the increasing and decreasing intervals out of this. I will also get maxes and mins, but I will get maxes and mins using the second derivative test as well. That's pretty fun. So we go negative infinity up to -1. We go -1 to 5/3. And then we go 5/3 to infinity. Okay, one other warning here. Polynomial functions are very predictable, very like off and on, plus minus, plus minus. Other functions are not necessarily that way. Okay? So just be aware of that as you run through these. It's okay to have a plus plus minus or a minus minus plus, okay? And if you have a plus plus minus, if you have 2 pluses in a row, that breakpoint at -1 is not a max nor a min. It's a critical point, but it's not a max or a min. If you go back to our definition, it's a max or a min if it's a critical point and there's a change in the sign on the derivative from positive to negative or negative to positive. That's really important. I'm going to keep stressing that. And come up, but just be aware of that. Hopefully you'll remember this discussion. Okay, so f prime. Let's go up here, look at f prime. I'll box it right here. That's f prime. Plug in an appropriate value here, maybe a -2. Can we do that? -2, 4, that's 12. Plus 4, that's 16, minus 5, I'm getting positive. You get the same thing. It's positive there. And then if I plug in maybe 0 is a good one here to plug in. If I plug in 0, I get negative, and if I plug in maybe a 3 there, it goes back to positive again. So let's answer our question about increasing and decreasing. So an increasing interval for our original function, we can write it as a union of two intervals. So I've got open, negative infinity to, remember it's closed here, -1, because -1 is in the domain of the original polynomial function. Union, closed, 5/3, comma, infinity open. So there's my increasing interval. Okay, that's my increasing interval. You read it right off of the table, where you see the pluses. How did I know this was positive? I plugged in a number in here to f prime. What allows me to do that? A cool calculus rule that says on this whole interval from -infinity to -1, no weirdness. It's either always increasing or always decreasing. No weirdness. The weirdness happens at endpoints and critical points. Okay. So decreasing, super formal definition here, weirdness, but decreasing from -1 to 5/3. -1 to 5/3. And then you could answer the question about relative maxes and mins too. We could do that now if we want. And then we can answer it again with the second derivative test. So max, where do we have a max here? There are two of them, huh? No, we have one of them, sorry. Got -1. So it goes positive to negative and then negative to positive. So we have a max at x equals -1. We have a min at x equals 5/3. And then we go and we do a similar type of process with the second derivative. We set the second derivative equal to 0. We solve for x. X equals 1/3. Make a little table here. Write sign of f double prime there. That's what we're checking. We have an interval that goes from -infinity to 1/3. And 1/3 to infinity. And we plug in a point. So on that -infinity to 1/3, I would plug in 0. When you're plugging in 0, I'll box it here. You're plugging in 0 there. Isn't that nice? That's pretty nice to plug it into a linear function, right? So plug in 0, you get a negative. And then you could plug in maybe 1 here and you get a positive. So concave up interval. Concave up is 1/3 to infinity. Concave down is -infinity to 1/3. Point of inflection. There's only a point of inflection if there is a change in sign in the concavity. It's analogous to this. There's only a max or min if there is a change in sign from one column to the next. Okay? It's the same thing here, and there is. There's a change. So point of inflection at x equals 1/3. Okay? So how could we figure out that -1 right here is the max based on the second derivative test? What the second derivative test says is f double prime, if I test it at -1, so f double prime tested at -1 would be 6 times -1 is -6 minus 2 is negative, let's see, 6 times, it's -8, which is less than 0. So if f double prime of -1 is less than 0, then that makes it a max. And really the way I think about it is because f double prime is negative, it's concave down. So it is makes it a max. X equals -1 is a max. And then the second derivative test for f double prime of 5/3. What does f double prime of 5/3 equal? 30 over 3 is 10. 10 minus 2 is 8. I get positive 8, which is greater than 0. So that means x equals 5/3 is a min. And so the second derivative test can be used as well. And that's what I'm doing in blue there. The second derivative test. You're just taking your critical points, plugging them into the second derivative. And if it's negative, it's on that concave down section, and it's the highest point. It's the max. If it's positive, it's on that concave up section, and it's the min. That's the second derivative test, if you'd like to use that instead of the first derivative test. Okay, so that's it. Okay. Really, 5.1 to 5.3 all go together. They're all tied together nicely. This is your capstone problem, I guess.